I grew up with one and only dream: get off this rock.
Sending power via lasers.
If we are, in fact, just a virus desecrating our home environment,
we're gonna send Mike an email, and we're gonna send him a screenshot of what we're doing.
We now know that most stars have planets.
Welcome to the Engadget Show. My name is Tim Stevens. I'm editor-in-chief of Engadget.
My name is Brian Heater. I'm standing next to you. That's my main job. I'm also standing in front of that giant thing right there.
Yes, we're at the Kennedy Space Center here in the east coast of Florida, where NASA launched many historic missions right over there.
Also, coincidentally, this happens to be the space show. What are the odds
Funny
of that? We've traveled all around the country. We've talked to a lot of commercial space companies, people like space elevators shooting lasers at things with the batteries.
Yeah, we're going to be taking a look at private companies doing space exploration and government agencies doing it too.
Yeah, I know a lot of people have been talking about how space exploration has been slowing down recently. Obviously, the shuttle program shut down, but I think that just means it's a much more exciting time. A lot of people are getting into the act right now.
You know what else people are talking about?
John Roderick.
Yes.
John Roderick.
John Roderick, indeed.
Yes. And you know what John Roderick's talking about?
Space.
Space.
Mary Roach also going to be talking about space today.
Yes, these are the voyages of the Engadget Show.
Engage.
We're going a lot stronger with this string than we probably need.
A
because
1
we
mile
have
an hour wind that's just doing this, okay, no big deal. But now it's doing it over 7 kilometers. That's how many pounds of pressure?
I'm Michael Lane. I'm the president of Liftport Group. We're the guys building an elevator to space.
This was the first real one I built. When I started talking to Michael about this whole space elevator thing, I thought it was a little crazy, but okay, I read a lot of science fiction. I understood the concept.
You have a ball and a string, you're spinning it over your head, the string in the middle stays straight, yeah? All right, so now just expand that to an Earth-sized system. The Earth rotates, and you have a counterweight, a satellite deep out in space with a very long string attached back to the Earth, right? The mechanics are the same, that string will stay straight. So if you do that, you could then clamp a robot to the edges of that string and climb up and down into space.
The crux of the entire problem of the space elevator is, can it hold its own weight? And there's no material that we could do for an Earth-borne space elevator that can hold its own weight over the distance it needs to be.
It's never been done before, so every action that we take, we have to kind of write our own rule book for. At least 5% of the entire Kickstarter budget is going to go into string.
And I saw this for the first time yesterday. I'm like, okay, well, that's different. Now what are we going to do? And we're going to try to make it work. And it might not. We're going to test some stuff.
You said you had a laptop?
Yep.
If you want to bring it out and hook it up, that'd be great.
There you go.
Is that a Pirate Bay sticker? Yep. Nice. My name is Otto. I work for communications with the Liftport Group. Yeah, is this Windows 8?
Yep.
Okay.
Kind of annoying.
That's okay. If you want to go to a control panel, so there's 2 different departments. One is the robotics department, and those guys are working on the actual robot itself. For us, we're the communications portion of it. So we, from the command center down on the ground, allow the ability for the robotics crew to communicate with the robot. Hey Don, did you want to point that antenna towards the hill? Hey, how's it going? So your radio's .2, right? Mine's .9.
And I just got your radio.
Today we're going to characterize the antenna. We have many different antennas we want to use, a Yagi antenna, omnidirectional, and we're going to see what our signal strength is and determine what we should use on board the robot, and then go from there. 4 to 6 millisecond delay.
I set you up to the max, the 28 dB.
Do you have the ability to do GPS on your phone?
Yes.
Can you give me? Can you record the lat long and the altitude, please? So there's engadget.com. So we're at 0.75 miles away from Site A, which has a internet connection, and we're at 25 megabits per second from this location. So we're able to bring up engadget.com as a fun demonstration that TCP/IP does work. But again, we're only at 0.75 miles. We have a lot further to go.
You start out as part of a NASA research team, and that was between 2001 and 2003. Then the Columbia crashed, and everything shook loose at NASA. Appropriately so, they cut about $1 billion worth of projects so they could get their birds flying again. And we were one of those that were orphaned. We kind of had a choice to make at that point. Take our research and just put it on a shelf and as my dad says, go get a real job. Or did we want to just keep going?
So we need the balloon to hold as high as we can, but we don't want to snap this thing in the process. It's a trade-off.
All right.
Oh, okay, that's 400 some odd, and this is supposed to be rated to 650. All right, so we're going to have to go to a larger system. You take the elevator, you poke the button, you get in the car. Well, this is the car. Well, we don't really think about this as an elevator. People say it's a space elevator. No, it's not. It's a vertical railroad. This is your train.
Lunar elevator, completely different. With different mechanics. So you've got the Earth on one side, it's big, a long ways away, the moon, small. About here is something called the Lagrange point. And the Lagrange point is basically where the moon's gravity and the Earth's gravity kind of balance each other out. And it's kind of considered an unstable position because it's like being a marble on top of a hill. If you fall this way, you're going to fall towards the Earth. If you move this way, you're going to fall towards the moon. Well, we can take that unstable point, sink a spike into the lunar surface with a thread, pull that spike through the Lagrange point, back towards the Earth, not touching the Earth. It's still a long ways from the Earth, but back towards the Earth. The gravity from the Earth will actually pull the whole thing tight, even though it's not touching, right? And that makes a complete system. Now you'd use rockets to access the lunar elevator, so we're still using rockets. But by having it, it allows for soft landing on the moon. We haven't had a soft landing capacity in roughly 30 years or so. What I think is really important is that there are 14 nations and more than 30 rockets that are able to go from Earth to low Earth orbit or Earth to geosynchronous orbit. Those same rockets could rendezvous at our Lagrange point station and use our robot to go back and forth. So suddenly you're saying, instead of it being really an American project of going to the moon, suddenly 14 different nations could go back and forth.
It's on that ridge line.
So straight
See
up,
that lump of trees?
that's where he's at, right in the lump of trees. Imagine all those houses out there being a bunch of stars. That's all their Wi-Fi routers.
And he'd be a satellite.
Ours would be a brighter one than all of them based on the amount of power that we're projecting. We got ping? It's one of them. Outstanding. What's our milliseconds? We're 2.5 miles. 4.1 kilometers. So let's pull up a website. Yeah, we have a lot, really good internet connection here. All right, so who wants to send the first email? Oh, Michael, let me give him a call.
Message has been sent.
Okay, let's give Michael a call.
Yeah.
Copy that. We're done with our test, and we sent a email from the top of the mountain over the Wi-Fi through the internet to you.
Tell him we want him to reply to it.
We would love for you to reply to it so we can make some history.
This Lagrange point station, I think that's the stepping stone to everything else. Everything else. You can build space-based solar power systems from here and provide clean, green, limitless energy to everybody on Earth. You can build biolabs, and you can build satellite repair facilities there. I believe it's going to be the most valuable real estate in the solar system. So all I'm going to do is I'm going to snug up so that it's basically tight, and at that point We're going to pull until we either pull the bumper off, move the box, or more likely break the string. And so we're just trying to test how much pull we've got on the string.
This is 1,000-pound string coming taut.
I'm going to hit the
If you
gas
want to
until
just
it
break
breaks.
the string,
I'm going to do that. I'm
Okay.
just gonna hit
It's
the-
probably going to pull the knot through. Go ahead.
1230? All right, good. Usually what happens is the knots are kind of like the weak points.
The string is it's distributing the load evenly across itself. This is the point where it's actually taking all the weight.
And that's okay, that's kind of normal.
This is where we go down and find a nice longshoreman to help us out.
Yeah. My passion, the whole reason I've been doing this for so long is I want to get humanity to start moving out to Mars, out to the moon, out to the stars.
I grew up with one and only dream: get off this rock. I'm blind in one eye. I've had arthritis. I've had an enlarged heart. I'm never getting off this rock by NASA. I could take an elevator ride though.
This is probably enough to build the entire lunar elevator that is human rateable. It's kind of mind-boggling to me that this is what we're talking about, but the math is good. I mean, I'm kind of cheesy by saying it looks good on paper. We still have a long ways to figure this stuff out, but yeah, I'm pretty excited about that. When we go and do our Kickstarter campaign, we're actually going as high as 7 kilometers. It's going to be the highest thing in North America, the tallest man-made structure ever, so we're pretty excited about that. For the lunar elevator, it's an $800 million project, and it's probably doable within about 8 years. I don't expect to raise $800 million off of Kickstarter, but since then I've been thinking about that. And I don't know if Kickstarter is the right mechanism, but we wiped out polio from crowdsourcing, right? March of Dimes. I only need 800 million over the whole 8 years, right? So, I mean, I'm being sarcastic, but in terms of, you know, is there a place for citizen scientists to take an active role in making a difference in the world? I think that there probably is. I think we can crowdfund an elevator on the moon.
Elevators on the moon, Brian.
Elevators to the moon, elevators from the moon, elevators everywhere.
But now we're back to Earth, and we are at NASA's Swamp Works, which is basically like the Skunk Works of yore, where they did lots of high-tech research projects, but now a little bit more swampy.
Yeah, and this cool old International Space Station Center. There's a lot of history happening here.
There is a lot of history.
future. A lot of things in here are going to be on Mars
A
at
lot
some
of cool
point.
stuff. After you, sir.
Oh, thank you. Let's go to Mars.
Let's go to Mars.
We're standing in the KSC Swamp Works. It's our version of an innovation lab. We brought in hand-picked innovators from across KSC. We brought their work with them, and we put them in a new environment to work on a lean development rather than having meetings and documents and requirements. It's idea, make it, build it, and go with it. Our focus is exploration. We work on all things regolith. Regolith dirt, space dirt.
Anytime you go somewhere in space, if you want to land there, you're going to have to land on regolith with rocket exhaust. You're going to have to drive on regolith, dig, process it for resources, build with it, and then study it for science. So that's what we do. You can use it as a building material, so we're starting to work on additive manufacturing on a very large scale. We're working with collaborators at the University of Southern California, for example, to do 3D printing of entire buildings in space. If you use the resources of the moon and Mars to do a mission to Mars, then you can reduce the mass of the hardware required for that mission by a factor of 3 to 5. If we can reduce the cost of a Mars mission by a factor of 5, that means we can do 5 times as many Mars missions. What I've got here is a piece of the Surveyor 3 spacecraft. Surveyor 3 sat on the moon for 2.5 years, and then Apollo 12 landed 160 meters away from it. And they brought pieces back so that we could study how the space environment affected the materials of the spacecraft.
The further you go into the solar system, the more resources you find. There's actually billions of times more water in the solar system than there is on Earth. In fact, Europa is suspected of being completely filled with an ocean that's 3 times the size of the ocean on Earth. So there's a lot of water in space, and if we can harness that water and use it, then we can live off the land and we won't have to bring it with us. All of our goals are to have these waypoints, these spaceports in space, where you would have propellants waiting, and your spacecraft would go from one gas station, if you will, to another gas station located at strategic points in the solar system where these resources exist.
So this is the actual tool that would go collect the regolith and bring it back to a processing plant. It's a lot like you're trying to build your base in like Command and Conquer and other things like that, and you got your tools that go out and get your resources and bring them back to you.
We need interfaces between excavators and manufacturing plants. So this is one of our interfaces, will be a feed system where this Razor excavator would drive up here and dump the regolith into this trough. This trough would separate any of the large rocks, and we would transfer the regolith that we would want to process into this oven. We would actually bake out the water from the regolith, and once we got the water baked out of the regolith, we would transfer that water to different devices.
Looks like somewhere in the 2030s is when we could have the mission that would take the ascent vehicle land on Mars, and then 2 years later have the human crew land nearby. We would start the process using a robotic system that would land on Mars automatically, and it would have a rover that would go out and dig the soil like the Razor, and that would deliver it to the transfer device. This would be operating for like a year on Mars, while the astronauts on Earth waited for the fuel tanks to get ready and for the launch window to open up. We can only get to Mars every 2 years or so. We would be providing the fuel that we get the crew back once they've explored Mars for about a year and a half, and then they would get back to the Earth by using the propellant that we didn't have to haul from the Earth ourselves.
During the Apollo missions, dust went everywhere. The dust was a nuisance during those missions. It would become more than a nuisance for the Martian or long-duration lunar missions. It could present health issues, but it would also affect the functioning of instrumentation, cover solar panels, and so forth. So to mitigate that problem, we developed a technology that uses electric fields that we generate on the surface of materials. We are implementing the technology to protect all kinds of surfaces, including astronaut suits and gloves, optical systems, camera lenses, spectrometers, visors, windows, and so on. Very transparent. I have the same panel here, and I'll use a simulated lunar dust to simulate exploration activities on the moon or even Mars, where we kick up dust, uncover a solar panel or a camera lens, and when I activate the system, you'll see how it moves the dust from the area where the electrodes are located. It also works as a deflector of dust, so if I leave it active and attempt to deposit dust on it, it'll simply deflect it.
We're inspired by the history of the building and what took place here, and we feel like we're keeping that, we're building on that legacy with future human and robotic exploration of the solar system.
We're going to Mars!
Yeah, when are you buying your ticket?
I'm thinking maybe 2013.
I think I'm going to buy a little early, try to save some money. Maybe around 2025 I'll put my money down.
I'll just keep checking back on Space Kayak.
That's the way to go.
We've been doing a lot of traveling lately. We went to the Jet Propulsion Laboratory to talk to Tom Rivellini. He's the 7 Minutes of Terror guy.
Yeah, we learned more about the creation of SETI and the discovery of 2 new moons for Pluto.
It's true. We went to NASA Ames in the Bay Area. They're doing a lot of interesting stuff with exobiology, which is life from outside of Earth. And something I've noticed across all of these pieces, people are just really happy to be doing what they're doing.
Aren't you happy to be doing what you're doing, Brian?
I am, and I'm happy to watch these pieces that are coming up right now.
My name is Tom Rivellini. I work at JPL, and I'm a principal mechanical engineer. JPL is one of the NASA centers. We're actually a federally funded research and development center, and we are contracted to NASA to manage and to execute spacecraft and instruments for planetary exploration. A big chunk of our work is in developing spacecraft to go to Mars. The 7 Minutes of Terror is a fun name that has been given to the whole entry, descent, landing process, because it literally takes just under 7 minutes from when the spacecraft hits the top of the atmosphere at Mars to when it actually makes contact with the surface. For starters, the first couple minutes is just going from 13,000 miles per hour down to a couple thousand miles per hour, and you're scrubbing off all of that kinetic energy in the form of heat. And so your spacecraft gets just tremendously hot on the front side, and we have to design about an inch thick material to be able to handle those thermal stresses, and that's pretty significant. It's a very sobering part of this job that if you make a mistake, chances are, if you make a reasonable sized mistake, chances are you're going to lose an entire spacecraft. The way we wind up developing our spacecraft, at least for our Mars missions, where it's impossible to do an end-to-end test. We'd love to be able to do that, but it's impossible to do that because there's so much is different. What we do is we generate very, very complicated simulations, computer simulations of the entire dynamics of the flight system. And then we go and isolate various parts of that simulation when things happen, when the parachute deploys, for example. We'll simulate that, but then we'll go off and we'll do tests. We'll make the tests as realistic as we can. We'll make the conditions as realistic as they can, but we understand that there's limitations. And so we'll go through the entire system and we'll test everything in piece parts, but we can never test the whole thing end to end in one big long string. And so we've gotten pretty good over the years in understanding what parts are more important to test than others, what parts need higher fidelity when we test than others. And that way we don't wind up spending exorbitant amounts of money, and we can use our limited budget as effectively as possible. Having said that, the ambition of the science community and the ambition of the public in general grows. For example, on the Mars exploration, every step that we've taken since Viking to Mars Pathfinder, the Spirit and Opportunity rovers, and now Curiosity, the amount of data, the amount of science, the amount of knowledge that we learn just keeps growing exponentially. But now the expectations of the science community grows also. And so there's a balancing act between what we can afford to do and what we want to do. And that consumes a lot of time with the leadership around NASA and JPL, is trying to balance those priorities.
My name's Greg Schmidt, and I'm the Deputy Director of the NASA Lunar Science Institute. We have a science directorate that does everything from study origin and evolution of galaxies. And then from that, we do a lot of aeronautics, which of course is why we're here in the first place. I think exploration is part of the human spirit. I think that perhaps is the most fundamental reason that drives us.
I'm David Morrison. I'm a NASA space scientist, and I also work at the SETI Institute. I think astrobiology is one of our primary motivations because we see that there are 3 things happening now that could lead us to answer the age-old question about life in the universe. The tremendous discoveries by the Kepler spacecraft of more than 3,000 other planets, and estimates that there are billions of Earth-like planets in our galaxies. Mars, as we study it, seems more and more like a planet that if it doesn't have life now, it certainly did in the past. And then you never know when a radio signal might be picked up. So I figure within the next 25 years, say, at least one of those 3 approaches is likely to succeed, and we will for the first time find evidence of other life in the universe. For a long time I was called Dr. Doom because I was concerned about asteroid impacts. The main problem with an impact is really the indirect side effects. Sure, if you lived anywhere near where it hit, you'd be in really bad trouble. But how do you get a global problem? You do by excavating huge amounts of dust from the impact crater. It goes into the stratosphere, spreads around the world, blocks out sunlight, temperatures drop, photosynthesis stops, and most life dies. Well, fortunately, we know there's no object out there that could hit the Earth that's as big as the one that killed the dinosaurs. The beauty of a survey is it allows you, once you've discovered asteroids, to project their orbits forward for decades or even centuries. And that is the key to any planetary defense. We're not going to mount some sort of last-minute defense. If we're going to do something, we have to have decades of warning. And then there are several things that could be done. The most obvious is to send a spacecraft out and simply impact the object and slightly change its orbit. And so far, we've found almost 10,000 of these near-Earth asteroids whose orbits could bring them close to the Earth. And fortunately, when we project those orbits forward in time and calculate where it will be, not one of them will hit our planet, at least not in the next couple of hundred years. So we're a lot safer than we thought we were before we started this survey.
The fundamental thing is we at NASA pushed barriers because space, it's just incredibly inhospitable up there. And in order to have people live there, even sending robots there, we have to do a lot of thinking and figure out some pretty innovative solutions that for problems that just don't exist on the Earth. And because of that, I think that it's pretty natural that those solutions are going to have applications elsewhere. A dear friend of mine, her father was diagnosed with brain cancer. She said that she was in his hospital room one time and she looked around at all the technology that was surrounding her and she said, my God, this is all from NASA. From the computers to the sensors that were being used to, you know, any number of different technologies.
We see so many opportunities, so many possibilities, but it's not in the NASA budget. Probably the most important place to invest is in areas related to education. I don't mean just going out and teaching classes, but providing opportunities for young people in science and engineering. That's where NASA has its greatest impact in improving our capability as a country or as a whole world to do high-tech things and live successfully in the high-tech world.
I'm Frank Drake. I'm a senior scientist here at the SETI Institute. And I founded the program of SETI, Search for Extraterrestrial Intelligence, 63 years ago. Yes, it's not just SETI. We have at least, it changes from day to day, 60 projects going on, only one of which is SETI.
My name is Seth Shostak, and I'm senior astronomer here at the SETI Institute in lovely Mountain View, California. The SETI Institute is interested actually in three areas of activity. I mean, one is SETI, of course. The second is astrobiology, just finding life that's maybe not so intelligent, microbes on Mars or the moons of Jupiter, all right? That's actually the biggest area of research here. And the third activity is education.
I'm Jill Tarter. I'm the Bernard M. Oliver Chair here at the SETI Institute, and my job is to be the chief cheerleader for our efforts to observe for evidence of extraterrestrial technologies. We really do want to have the public come along with us in this exploration. We'd like to engage them on a number of different levels. SETI at Home has been going now for over a decade. It was developed at UC Berkeley. It uses the same sort of pattern recognition algorithms that we use in our search here at the SETI Institute. The difference is we do our search in real time.
We always have an observer on duty. And when we get such a candidate signal, the system, the computer notifies us there's a candidate signal. And we immediately do tests to see if it's moving with the stars, if it's turning on and off. We search for signatures that will only be present with a true extraterrestrial intelligence signal.
We've launched a citizen science project called SETILive.org. And the live piece of that emphasizes that what we're asking people to do is get involved with data coming off the telescope as we observe. We are, in a sense, using people as computers, but really what we're trying to use is their phenomenal pattern recognition capability.
My name is Mark Showalter. I'm a senior research scientist at the Carl Sagan Center of the SETI Institute. The way we think about the Institute is that on the research side, if you can argue that you have any place to play in the Drake equation, then you have a place at the SETI Institute. It has to do with how many stars are in the galaxy, how many planets per star, how many of those planets have life, how many of those planets have intelligent life, and so on. So my position is studying the dynamics of rings and moons of mainly the outer planets of our solar system, but these are dynamical analogs for how galaxies form and how other planetary systems form. So my role in that organization means that I can basically talk about how it is that planetary systems come into being, which seems to be one of the critical steps before you can get planets and then life, and then intelligent life, and then radio communications.
So in a million star systems, you're going to have enough winners and enough time on those planets to have allowed life to evolve to the point where it's able to, build a radio transmitter.
We're looking for people who construct technology like as we construct. And if it's made by an octopus, that's okay with us. It's just as good as if it's made by something that's human-like.
So Brian, this is where the world's media would gather to watch the shuttle launches that happened right over there.
These bleachers, like NASA's shuttle program, have seen better days, Tim.
Yeah, indeed they have. But back before they launched, they had a lot of things they needed to figure out, things that they needed to solve before they could go into space. Things like, how do you poop up there?
Yeah, where do you vomit up there? All sorts of gross things like that. And when I'm talking about space poop, Tim, there's only one person in the world I'd like to speak to.
Who's that, Brian?
It'd be Mary Roach, the author of Packing for Mars. We spoke to her about puking and pooping, mostly.
My name is Mary Roach, and I'm, people call me a science writer. And here's science now. Hello. Hi. Okay, my name is Mary Roach, and I'm a science writer, and I write about it's kind of unusual aspects of science and medicine. My first book was Stiff, The Curious Lives of Human Cadavers, which is kind of a book about interesting post-mortem careers. One of the things that came up over and over in Packing for Mars was just any machine or piece of equipment that works here on Earth in Earth gravity doesn't work in zero gravity, has to be rethought, retinkered, completely redesigned, and that includes the toilet. The Gemini and Apollo era, I had no idea. NASA didn't talk about this a whole lot. It was really sort of the mythical, heroic, larger-than-life astronaut in his big puffy suit. And it was very, the nitty-gritty of what that was like was kind of left out. And it was amazing. You look back through the mission transcripts about what was really going on, and a plastic bag with an adhesive ring. The food was designed to constipate the astronaut. It's just hovering, so this is the horrible part. You had a finger caught, little like glove finger, and you'd have to like coax it down into the bag. It was all low residue, that's low residue. NASA waste management system people came up with just the most spectacular euphemisms, like there's ingesta, egesta, the material. My favorite was the astronaut's contributions. Airflow, toilets, it's like sitting on a shop vac, kind of like pulls it away. You gotta know, okay, how much airflow? Is this really gonna work? You gotta put it on the Vomit Comet, which is this plane that does this parabolic flight path, and as it goes over and down, you have 22 seconds or so. I found this guy who had been testing the toilet, and there's these guys in the other end of the plane, and he said, yeah, they had a curtain drawn, and you could tell what was going on. You'd see, they'd see their feet come up off the ground, and then you'd hear everybody going, go, 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 go. Because the poor guy, he's got 22 seconds. Think of it. And he failed, the guy failed. The most stressful possible, and with an audience, come on. There's nothing like a manned space mission to a place that no one has ever been. I think that it would be kind of awesome. And I absolutely understand when somebody says we have so many problems and we have so much debt in this country, how can you possibly talk about spending billions of dollars on a manned Mars mission when you can use robotics and you can do the science over time get the same answers, maybe a little more slowly. And I absolutely understand that perspective, and I sympathize with that, but my feeling is that if you take the money away from space exploration, if you can guarantee me it's going to be spent on education, or it's going to be spent on a cure for cancer, it's going to be spent on something kind of noble and worthwhile, I would say absolutely spend it there, but it never is. It's just squandered on something. You could kind of think outside the box with a Mars mission. You could, and some of this is going on now with this Mars One, which would be a one-way mission where you would send people to Mars and you would keep them supplied and they would stay there. You wouldn't. The tough part is bringing people back from Mars. So you send them there and you keep supplying them, and they do science the rest of their lives and they die there, and there are astronauts who would love to go. And you could also have it multinational, where there's lots of people contributing money. It doesn't have to be NASA, it doesn't have to be just NASA. You can also, what Mars One is trying to do, get the entertainment industry involved. They kind of do like an American Idol. You can go to Mars. One of the people on the mission will be chosen by by viewers around the world. So everybody can apply, everybody has a chance. And then you could, using the rights, entertainment rights. You send a geologist with a lot of knowledge and intuition, they can kind of just at a glance say, I know what was going on here, and save you, decades worth of sending rovers. But it's really about the excitement and inspiration and kind of getting people jazzed about science. I think of myself more as kind of a gateway drug to science for people who don't think science is interesting or don't think they're interested in it. I kind of try to make it fun. And the next book has to do, it's called Gulp, Adventures on the Alimentary Canal, so it's all sorts of weird shenanigans between here and here. Honestly, I don't know what's next. I've kind of used up the human body, and but Packing for Mars was the human body in unusual circumstances, so I may go off in some other unusual circumstances, and I'm not sure where I'm going.
I spend a lot of time wondering what the point of it is, what the point of everything is. At any point, at any given day, I wake up in the morning and I think, I should get to work today. I should write something, or I should make some phone calls. And then I inevitably follow a progression of, well, what's the point? What's the point of calling that guy back? He just wants me to do something. He just wants me to do more work, make his life easier. And eventually, I asked myself, what is the point? All the way back to the question, which is, what is the point? What is the point? Human beings are just slugs, and we're just gobbling up our environment and replacing fecundity with big piles of poo. And then I think about outer space and space exploration, and I think, well, that seems reasonable, that if we are, in fact, just a virus desecrating our home environment to the point that we can't live here anymore, why shouldn't we go out in space and become a super space virus? Human beings could potentially be the scourge of the universe. That could be the point. It could be our destiny. We are the ruiners of the universe. This seems like a reason to get out of bed in the morning. This seems like a reason to call a guy back and to do whatever dumb project it is that he's asking me to do for free. Because I am furthering the cause of the greatest space virus of all time, potentially.
So how great is John Roderick?
John Roderick is pretty great. His second appearance in the Engadget show, and I don't think it'll be his last.
Yeah, oddly, we didn't even ask him to be on the show. He just showed up on a doorstep with a little sign asking if he could do a segment.
Pretty good dude.
We still have a ton of show left. We kind of went all over the country and got some space stuff.
Yeah, now we're kind of transitioning away from what is ultimately becoming the past of space travel, which is big government-funded stuff, and more into the future, which is more private.
Yeah, obviously the shuttle program has kind of winded down over the last couple of
sadly.
years. I don't know if it's sad though, because we're seeing a lot of really exciting companies come out, and a lot of that is being led by Google and the Lunar X Prize.
Yeah, it's basically a private prize to encourage people to go to space, which harkens back to the early days of aviation, where there were prizes to fly across the Atlantic and things like that, and now there are prizes to get people up there.
Yeah, and a lot of this is also sort of taking the software route too. We talked to a VC company out in Seattle, Space Angels. They're funding a company that shoots lasers.
Is that
to
a
keep
sequel
drones in the
to
air.
Barbarella?
Yeah, in space, no one can hear you ring a bell.
Hmm.
We also talked to a couple of companies. They're making some space suits. This is a really interesting area actually, because a lot of these companies actually started out making spacesuits for movies.
That makes sense, I guess. I mean, if you're a private company, you need a spacesuit, who are you going to call?
Well, not Ghostbusters, unless there's some kind of space ghost problem.
Sounds like another great 70s sci-fi
yeah,
movie.
Coast to Coast.
My name is Alex Hall. I'm the Senior Director for the Google Lunar X Prize. If you look back over the history of time, you discover that, major advances in innovation and technology and solving problems have come about through prizes. The Google Lunar X Prize is the largest incentive competition of all time. We often joke that we're like the Lunar Chamber of Commerce. We're out there on behalf of all these teams, and we're trying to persuade the rest of the world that there's going to be business opportunities, that there's going to be science opportunities, that there's going to be media opportunities.
We're Astrobotic, which is a spin-out of Carnegie Mellon. Now this really got started in around 2008 after the announcement of the Google Lunar X Prize, which promised 30 million prize purse for landing on the moon, driving 500 meters, or hopping 500 meters, and then sending back high-definition video. What we're looking at is a series of robots that are going to land on the moon in 2015 to find water at the pole. We started out with an idea that we'd go to the equator of the moon. It's over boiling temperatures during the heat of day, and during at night, it's the temperature of liquid nitrogen. So the first robot that we developed had solar panels on all the sides and radiator on all the sides. This design did not work, and we found that out. The side that you're taking in power on, that you're also trying to reject heat from, gets too hot. So we went to an asymmetric design, which had the solar panels on one side and the radiator on the other. Today, our program is looking to build a rover that's going to the pole of the moon. Now, on the pole of the moon, the sun comes in at a glancing angle, about 5 degrees, all the time. So solar panels are vertical. In fact, the shell of the robot I'm speaking about is apparent in the background here. It's likely that there's a substantial water content in the pole of the moon, so you can do incredible things with that. You can produce energy from it. You can make rocket fuel from it. There's even valuable metals that are in the soil of the moon. So there's a potential resource market from the moon. We just don't know today. Right now, we don't have a way of shipping a good to the moon. You can ship a good anywhere you want on Earth, but it doesn't exist for the moon. We are well poised to be the ones that are first ones to develop that commercial transportation market to the moon. So the Polaris robot is the payload robot that's designed to carry about 67 kilograms in its rear compartment, but also has all the technology and components necessary to go after the Google Lunar X Prize. And we think if we do it right, we can go after both. This is our lander. So this is the workhorse behind all of the rovers that we just talked about. We put this together last year, and this is sort of a mix between prototype and flight qualified components. The deck, the cones, the bottom here, we call this primary structure. We've taken that through qualification. That's actual moon hardware. So that stuff we're absolutely going to fly to the moon. So the lander itself is about 800 kilos. It's massive, and when it's fully fueled, the whole stack up is about 5,500 pounds. It's massive, and most of that is actually fuel. It's a one-way ticket. There's no coming back for this guy. What's really cool is that the space shuttle just retired. And because that was a well-stocked program, one of the tiny maneuvering engines that was in the rear of the space shuttle is perfect for the main engine of this craft. So we're going after it as the main engine. The space shuttle will have a new life in commercial space.
In the missions that have followed Apollo, we have learned so much about the moon. We have learned what its likely origin is, we've learned about what it's made of, we've learned about where all those resources are deposited in the lunar crust. So if we can find those resources, the things that make rocket fuel, the things that make spacecraft, on the lunar surface and mine them and process them there, then that already makes it far more efficient and far more cost-effective in the long run for us to be exploring the solar system and moving further out. Part of me, and one of the reasons I'm excited to work for the X Prize Foundation, is that they're working on things that will help us understand why do some people live to be 100 or more, these kind of things. And so I look at all of that and I'm like, if those guys with that prize can figure out how we live longer, then maybe I can live long enough to the point where space comes down to my budget.
I'm Tom Nugent, and I'm the president of Lasermotive. The idea of power beaming has been around for decades, and it was only starting in the 90s and then into the 2000s when the lasers were becoming powerful enough and cheap enough and efficient enough to really be useful. Lasers have been around for a little bit more than 50 years, and they've been used in telecommunications as a lab tool, and it's only recently that they've been used for things like welding and cutting, and now for us, transmitting power to be used remotely. And so we think that's going to kick off a lot of applications. We've been internally funded from our members. We've had contracts and the prizes from NASA and are working on getting some contracts from the military for some of these applications. And we've been going out to the investor community. So sort of spanning the gamut of different ways of getting the funds necessary to propel this forward. As one example, the Space Angels Network is comprised of people who have a focus on aerospace. They understand that world and can look to some of those longer-term space applications.
I'm Joe Landon, and I'm the Managing Director of Space Angels Network. Space Angels Network is a global network of angel investors, and our members are focused on investing in early-stage aerospace and aviation startups. This is a company that has a technology that can be applied to other problems today, problems more down to earth. Today we think of space as something separate from what we're doing in our everyday lives, but more and more space is becoming a part of our lives.
That little toy helicopter has no batteries on board. There are two little photovoltaics on there that are getting light from a laser down here and are hardwired into the motor. So if I turn off the laser, the electricity stops and it stops flying. Turn it back on, I can change how much laser power we're getting and change how much power is going to the motor. We retrofitted the plane with our laser receiver panel, did a series of tests here in the shop in our wind tunnel, flying it for 48 hours continuously to make sure that everything would operate for that long, since normally it flies for 2.5 hours. We have two lasers. One is out for service right now, the other one is back there. And each of these lasers puts out 2.25 kilowatts of light, which is about 3 horsepower of light. The beam is shaped through a series of optics, collimated on these spherical mirrors, and then bounced off of this steering mirror here. This is a 2-axis gimbal mirror that then directs the beam up to the target in the sky. For powering a satellite, I'm just going out to a longer range, collecting the light on a solar cell, and using that to power the satellite. To launch a rocket, what I'm doing is heating a propellant. The benefit, in addition to performance, is that you can launch smaller payloads much more frequently. So imagine a fleet of FedEx trucks instead of the very occasional tanker truck.
Taking cargo from Earth to the space station over and over again, maybe once a month for the next 5 years, that has already been done for the last 10 or 20 years. That's prime time for commercial space to step up and provide that service to the government.
Right now, when you're building stuff for space, you build very large structures here on the Earth, you launch them and put them in place. Instead, you could do a lot of that assembly on orbit by sending up all the pieces you need. You can send whatever supplies the people need on space stations the next day, rather than having to wait 6 months to get some part or some emergency supplies. You can put it on the next rocket that's going up the next day. So this power over fiber system is our first commercial product. And as I said, this is a stepping stone to larger systems that deliver more power over longer ranges. Flying robots, powering telecom towers, sending power to remote bases, and eventually sending power to space to launch rockets. And so we start with a laser that sends light out through a fiber optic cable. We have 200 feet of fiber wrapped around this spool here that then goes to our receiver. Inside here are some of the photovoltaic cells that convert that light into electricity. And we have a couple wires running off to this little quadricopter that's flying on electricity generated from this receiver that got light from the fiber that came from this laser. There may be a day when you'll power your phone by laser power, or maybe charge your laptop. It's a wireless extension cord. And so any place where you want to deliver power may be an application where the laser power can help.
Christopher Gilman. I'm the president owner of Global Effects, and I'm also chief designer for a company called Orbital Outfitters that does spacesuits for the commercial space industry. When the military or the government does something, yeah, they want a certain amount of aesthetic, but really it's about function and price and getting the project done. In the case of spacesuits in design, you have general public expectation of what something should be. So we have a number of companies making suits, but they're traditional aerospace. And in the traditional aerospace, they have a set way of doing it. We tell people at Orbital Outfitters, we have the cleanest sheet of paper, and we'll let you hold the pencil. And we'll take you in here to the Orbital Outfitters spacesuit room. And we currently have our prototype suit. One of the things you'll notice, we're talking about commercial design versus government design. You notice this helmet is very smooth and featureless. A lot of the aerospace helmets for the government, they have a lot of mechanics on the outside of them, and they have, multiple systems for safety or multiple systems from an engineering design. Whereas this does all the function that it needs to, but we've removed all of the extraneous mechanical bits and incorporated them in other ways so that you still maintain the safety, but you simplified the way the helmet works. So the way this is designed is the visor is locked. To unlock it, you push it in and unlock it, and it rotates up. Now when you're wearing the helmet, you just reach up, and anywhere you reach up here, you'll encounter that bar, and you just pull this down, and as it comes down, a mechanism moves the visor out and moves the visor forward and seals it against the seals. And yet there's no mechanics on the outside. So that's just one way that we try to take a design, incorporate all of the safety and all the mechanical requirements, but in a package that a person doesn't need to go through all sorts of specialty training to use.
My name is Ted Southern. I am the co-founder of Final Frontier Design, and we are a space safety garment manufacturing company here in the Brooklyn Naval Yard. We're working on spacesuits for the commercial space industry. The fabric has two sides. There's a coated and an uncoated side. So an IVA spacesuit is an intravehicular activity safety garment for space travel. It's contingency use, meaning normally it wouldn't be inflated, but the idea is that you wear it in case of an emergency loss of cabin pressure. We're really proud of this suit. It's sort of our intermediate step to what we're working on now, our 3G suit. There's some big changes in the next suit. The big difference is going to be the helmet. Instead of having a big helmet ring like this where the whole helmet comes off, we're going to have a retractable visor that's pressure tight.
My name is Nikolai Moiseev, and I spent about 26 years for spacesuit design. We have made a new generation spacesuit. This spacesuit has some advancements, lightweight, mobility, very comfortable.
And so on one side, we're building these IVA suits for commercial companies who need them. On the other side, we're building gloves in particular for NASA that have high mobility and dexterity and are inexpensive and lightweight. So this is a vacuum chamber glove box. There's a vacuum pump. This glove that we have here now is what we call our IVA glove. It's a single layer glove. You can see they're integrated fingertips with nails, very low torque in the fingers, very thin wall. Allows really great flexibility. Most spacesuit gloves is pretty hard to touch your pinky to your thumb. There's a palm bar on there, adjustable palm bar, and patterning for wrist flexion. This sort of underlines the challenge that we have moving from viable prototypes that function at levels that NASA needs into, certified manufacturing that can go into space.
We've come to the end, Brian.
Just the end of the show, not the end of space travel.
Yeah, we're standing in front of the iconic clock, which has counted down to so many shuttle launches in the past. Right now, it's obviously got nothing to count down for, but there's a bright future ahead of us for space travel.
This is the end of an era. Obviously we've seen a lot of really cool commercial space companies come up. People are going to Mars, there's space elevators, people are shooting lasers for battery power. It's future is bright.
Future is bright, and it'll be led by people like Mary Roach, we want to thank for talking to us today.
I would like to think that John Roderick's going to be the first man on Mars.
I think that's a pretty cool idea.
Very real possibility.
Let's put that Kickstarter to get John Roderick on Mars.
Yeah, I'm really excited for the future. I'm really excited. I think this time when we do the space show next year, it's going to be amazing.
I think it will be as well. And maybe the wind won't be so bad, so maybe my hair will be a little bit better. But we'll see about that. Brian, thank you very much for coming down to Florida with me.
Those Martian storms are a pain, Tim.
They are indeed.
Thank you, Tim. I want to thank you. I want to thank them.
Thank you for watching. We'll be back next month with another episode of The Engadget Show.
In space.